So this is a final solution for the forced damped vibration, and here the actual solution is displacement as a function of time is equal to capital X sine omega t plus xi, and x and xi are given like here, these quantities, and you know all of these quantities, you know k, you know m, you know c, you know omega. Omega is the forcing function, forcing frequency, and f is the amplitude of uh, forcing. So here if you see this equation for the maximum displacement, it looks similar to the electrical circuit where you have resistance, inductance, and capacitance. So the resistance to the motion is something K. K is similar to resistance because it resists the motion, it tries to bring it back to original position, and the inertia m omega square or inertia is similar to inductance. So the property of inductance is that when the current is moving, it keeps on moving. Uh, there, it overshoots its original position, so it is similar to inertia of the system, electrical system, and the damping is equivalent to capacitance c omega square, c omega. So it stores the energy and dissipates the energy. So here this both resistance are and inductance are on real axis. Resistance and inductance are on real axis, and capacitance is on imaginary axis. And the combination of resistance and capacitance is known as impedance, impedance of an electrical circuit. So you can draw similar analogy there, that you have a resistance, you have an inductance 180 degree, and the capacitance, and from that diagram you can get that the summation. If you get the equivalent diagram, you will get R minus I and C on the x-axis, and then R minus I whole square and C square is the impedance. So Z equal to R minus I whole square plus C square whole square root. So this is something similar to Z. So uh, so we get x equal to f by z, which is impedance. So impedance can be given by this quantity in the mechanical case, k minus m omega square whole square plus c omega whole square. And phase is the phase between the resistive and the capacitive component final output. This is the phase phi, and this can be given by the ratio of the perpendicular and the base. You can draw similar analogies here. Yeah, it helps to visualize better because if you have taken a class in electrical engineering, you have studied the alternating current. So our force damped vibration are nothing but similar to the alternating current. Now our equation for force damped vibration we can further simplify. We can take, let's say in this case we'll take the k outside. So the k square outside of this thing. So this is by k, and we'll get inside the bracket 1 minus m omega square k, and plus c omega by k whole square, and times I you will get as times I c omega by k by 1 minus m omega square by k. So this we will try to simplify from the known quantities that we have seen earlier in the case of damped oscillation. We know that k omega natural, the natural frequency is equal to square root of k by m. So the expression m omega square k becomes omega square by the square root of k by m whole square, that is equal to omega by omega n whole square. So this you see repeatedly in our equations, m omega square by k. And now for the critical damping is equal to 2 root over m and the Z damping ratio is equal to C by Cc, that is equal to C by square 2 square root of Km, and so uh, here if you if you multiply it by K and divide it by K, you will get Z is equal to C by K divided by 2 and root over M by K. The root over K by M is omega n, which comes in the numerator. You get omega n C by 2K is equal to. So C is equal to 2K psi by omega n. This is also a somewhat important formula. You can determine the critical damping value from the stiffness and the natural frequency and damping ratio. And this value, if you substitute in the expression C omega by K, that is we are seeing repeatedly in our solutions, then you will get C omega by K equal to 2K psi omega by K omega n. K will get cancelled out. So C omega by K will be equal to 2 psi omega, that is forcing frequency divided by natural frequency. So these values, if you substitute in and F by K, we have determined M omega square by K, we have determined C omega by K. F by K is equal to the deflection due to force alone, that we showed as Xs is equal to F by K during the start of the chapter, due to the force alone, where there is no mass, no damping. So you have X equal to Xx by 1 minus M omega square by K, that is omega by omega n whole square. So omega by omega n whole square, this thing squared, plus C omega by K, that comes to 2 Z omega by omega n. Now this thing also whole square. So this you get expression for X, and for xi you get C omega by K, that is equal to 2 xi omega by omega n square by 1 minus n omega square by K. So 1 minus omega by omega n whole square. So these are the expressions you get in the non-dimensional form. So here you can see that you have the quantities in terms of Z, that is damping ratio, that can be easily determined 2 square root of Km, and you have natural frequency, that is square root of K by M, that is also known. You have static deflection, that can be determined by the force, the amplitude of force divided by the spin constant, that is also easy to determine. And then you have the omega, that is the forcing frequency. So you can know the displacement and phase of the displacement with respect to force from the known quantities. Now for forced harmonic oscillation, it is convention to define this quantity x by xs, that is called the amplitude ratio, and this is equal to 1 by square root of 1 minus omega by omega n whole square plus 2 z omega by omega n whole square, and tan phi is anyway 2z omega by omega n by 1 minus omega by omega n whole square. So here you can see that these quantities are basically function of omega by omega n, ratio of real frequency by natural frequency, and z. So if you plot these functions on x and y axis, that is x by xs, and on the y axis you use omega by omega n, ratio of natural frequency, and you plot for different values of z, you will get curves like this. For different z, you will get different curves. So these are called forced harmonic oscillation vibration curves. So you get curve like this, and the value of 1 will be somewhere here, and this is greater than 1. This is then the force frequency is greater than natural frequency, and this side is force frequency less than natural frequency, and this say for z is equal to 1, like 0.8, and then 0.7, So like that, so here Z decreases. So as Z, that is the damping ratio. Damping ratio decreases as the amplitude increases. What happens when Z is equal to 0? There is no damping. So if you put Z is equal to 0 here, you will get the case, the equation for forced undamped oscillation. There is no uh, damping. So you get x by xs is equal to 1 by square root of 1 by 1 minus omega by omega natural whole square. So this case you see that when omega is equal to omega n, natural frequency, the forcing frequency is equal to natural frequency, x is infinity. So amplitude is infinity. So this is a condition which is called resonance. So now we can come to the definition of resonance when amplitude becomes infinity. That means that the force is applied just at the right time when the amplitude will grow. And again when the amplitude goes towards the negative, the force is applied just at the right time for the amplitude to grow. The amplitude will keep on growing infinitely and the resonance will occur. So this can damage structures very badly, and this is the condition that has to be avoided at all costs. So that's why I told you in the free vibration section that mm, uh, it is natural. It is important to determine the natural frequency, because if our forcing frequency is equal to natural frequency and it goes to infinity and the system damaged. Yes, so we should avoid this condition. So this happens in the case of forced undamped oscillation. In the case of forced damped oscillation, also the resonance occurs. Resonance occurs means the amplitude goes to a high value. That will depend on the value of Z. So the higher the value of Z, the lower the amplitude will be. And lower the value of Z, the higher the amplitude will be. This is plain common sense. So the but for a particular value of Z, there is a value of omega that will have maximum amplitude. So that is called resonance for damped system. So resonance for damped system, what it is, for particular Z, you have omega by omega n giving maximum amplitude. That is called resonance for a damped system. It can be controlled by increasing the damping, but still that frequency should avoid. What is that frequency? That you can determine by taking the solution of this equation, 1 minus omega by omega n whole square plus 2z omega by omega n square. Basically the denominator of this function by the way is also known as magnification factor. So you have a static deflection due to the forces, due to the dynamic forces, that is xs, and your real the amplitude will be magnification factor multiplied by the this displacement due to the force alone. It's called magnification factor. So if the magnification factor is infinity or x tends to infinity, the denominator has to go to 0. Denominator tends to 0. So this thing, if you equate to 0 and find out the solution between the relation between omega z and omega n, I'll leave the mathematical part for you on you, and we'll find omega resonance equal to omega natural 1 minus 2 z square. If you solve this equation that is given here. So this is the frequency at which the resonance will occur for a damped case, 2z square. In the case of undamped case, z is equal to 0, you will get 1 minus 0 square root of that, then omega n. So in the undamped case, simply omega is equal to omega n will give you resonance. In the case of damped case, you will get omega n 1 minus 2z square. There you will get the resonance. Now to see the condition for resonance, the resonance frequency is equal to omega n 1 minus 2 xi square. So if z is greater than half, 1 by root 2, then you will get omega r equal to 0. This quantity will be equal to 0. So there is no resonance when z is greater than 1 by root 2, because after that this value will become negative. You will not get any meaningful forcing frequency. So if you can maintain your z such that it is greater than, the damping is greater than 1 by root 2, which are 1 by divided by 1.414, I'm not sure, but there will be some value around 0.7, 0.8. If you by maintaining above that the value of damping, there will be no resonance. So this is an interesting observation in real system. Now what about the phase? The phase equation, you know, it is equal to tan psi is equal to 2 z omega by omega n divided by 1 minus omega by omega n whole square. If you plot this on this curve, I've drawn this a priori, you will get a graph like this. The phase will vary from 0 to minus 90 to minus 180 degree. So the phase will be negative. So displacement, so our real actual phase is the force. So this the whatever v you get, phi will be the phase of displacement with respect to force. So displacement lags the force because v is negative always. So the graph will look like that. When the value for the z is equal to 1, the critically damped case, it will look like a logarithmic line, and it will cross the axis at 1, omega by omega n is equal to 1. When z is equal to 1, omega is equal to 1, phi is equal to 90 degree. So the force and the x will be 90 degree apart. Another quantity of interest in resonance is resonance amplitude. So we know that we have a system, it is having stiffness, mass, damping, and it is subjected to external forcing of omega with force F. The resonance will happen, but what is the amplitude of the resonance that we can tolerate? That will help to determine our design limits. So against the frequency, the resonance will happen at some particular frequency that is given as omega natural 1 minus g square. So what is the amplitude here? So amplitude that we can define from the magnification factor mf x by xs equal to 1 by square root of 1 minus omega by omega n. Omega in this case is omega n 1 minus g square. So omega by omega n will be equal to 1 minus g square whole square root of that. This will be 1 minus g square whole square, and then square root of this full function, and then you have plus 4g square omega by omega n, again it is 1 minus g square whole square. So this function is square root of that. To simplify this expression, so it's all 1 minus 2g square everywhere, because omega is equal to omega n 1 minus 2g square. If you substitute here and then you simplify it, you will get this expression. In this expression, 1 and 1 will get cancelled out, and you will get 1 by minus 2g minus 4 g to the power 4 g to the power 4 plus 4g square minus 8 g to the power 4. Sorry, it will be plus 4 g to the power 4 because square is there here. 4 g to the power 4, 4g square minus 8g to the power 4. This will be equal to 1 by square root of 4g square minus 4 g to the power 4. This will be equal to 1 by 2 square. G will take outside 1 minus g square. So maximum magnification factor is this value. So the magnification factor is x by xx. It is maximum x by xs is equal to 2g 1 minus g square, and so this is just a function of damping ratio for resonance when the resonance occurs. So, and the formula for resonance is omega resonance is equal to omega natural by 1 minus 2g square for the force vibration case. So in case, obviously Z is less than one, can't be more than one. It can be overdamped also. So we are considering Z less than one cases only, where the resonance or the vibration will likely really happen. We are all talking about underdamped cases, and Z is less than one. So for cases where Z is very less than one, smaller than one, is slightly damped case, that will occur in practically all industrial application, because we don't want damping too much, because it means loss of energy. So slightly damped case, you can neglect this function, 1 minus V square is basically equal to 1. So you get maximum magnification factor as equal to 1 by 2Z. It's a simple formula to remember, that you should remember at resonance. So the omega is fixed. For a given mechanical system, maximum magnification can reach up to this value. Just divide 1 divided by 2 xi, the damping ratio. Now we have covered the topic of resonance, so we come to the next topic, that is vibration isolation. This is a configuration where typically we see in the industrial system that there will be some machinery there, and then it will be vibrating. There will be some inherent rotating unbalanced part, there will be some reciprocating part, so it will have some excitation, dynamic excitation. So you will want, due to the excitation, the amplitude can be very high, and the part can get damaged. So in that case, you want to limit the amplitude. So in that case, what we do normally is that we attach the mass, vibrating mass, with a spring and a damper. So this is called vibration isolation. So from the land that where it is supported, the machinery is supported with the help of spring and damper. So this function is called vibration isolation, and it is required so that the surroundings of the machinery, the land, the substructure where it is supported, they do not feel the excessive vibration. So vibration from machinery should be should not be transmitted to base. This is called vibration isolation. In car also, you see that in car your rotating component will have vibration, so that thing should not be transmitted to your body. In car particularly, you see this example, you have a wheel, and then on the road you have this kind of, you do not have a smooth road, you have some serrations. Because of that, some vibration will occur of the wheel. This wheel should not be supplied your car body. So there will be some springs here, some dampers here. Yes, that is what we call suspension. The suspension of the car is also a case of vibration isolation. Similarly, in the industrial machinery, you will see that the machinery is mounted on some springs and base. So the engines are also mounted like that. So the vibration from the machinery doesn't reach the supporting structure and cause failure. So in all these cases, we can divide the forces into basically two categories. One is the force on machinery, that is the machinery here, and other is the force on structure. So what we have analyzed till now for is the force on machinery. That we had a mass suspending from the spring and having a damper attached to it, and we are considering the motion of this mass, the forces on this mass, and this will be now M, the machinery. So we are not interested about the forces on the machinery now. In the topic of vibration isolation, we are interested in the forces on the structure. So force on supporting structure. That is what we are interested in now. Supporting structure. So now we are interested in force at this location, the supporting structure is supporting the mass M, the vibrating rotating machinery. The equations will remain same, the derivations will remain same. For M, you already know what is the equation of balance for force case and damped case, all of that cases, and you know the displacement and acceleration, all of this M. What is the force going to be on the structure? That is important in the topic of vibration isolation. So a structure will basically have two forces. One force is due to the spring and other force due to the damper. Only two forces. The acceleration and the excitation of the mass will not be felt at the structure because only damper and the spring is connected to the structure. So if you draw a force vector diagram for the structure, you have the spring force Kx, where x is the displacement of the mass at any instance, and the damping force as equal to C E x dash. The amplitude of the oscillation is x, so small x equal to capital X sine omega t plus phi. So magnetic amplitude of x is capital X, and amplitude of x dash is derivative of this function. This will be x omega cos omega t plus phi. So you have amplitude x omega. So the force due to the spring will come as kx in this diagram, and the force due to the damper will come perpendicularly to the because you have cos function here. Cos function is 90 degree apart from sine function. So the amplitude of the damping force will be Cx omega, and the resultant force will be the force on the structure. So the resultant force on structure will be equal to kx whole kx, the amplitude of x whole square, plus cx omega whole square. So this is the amplitude of force on the structure. Of course, the force on the structure will follow a sinusoidal pattern. The actual force will be F structure sine omega t plus phi, something like that. Because you're talking about vector x. Every discussion from vector x. So the transmitted force is equal to the force on the structure. The transmitted force is the force transmitted to the structure by the spring and damper system. From the spring mass system, the vibration isolation system. So the transmitted force will be equal to kx square plus cx k capital X square, amplitude of oscillation, plus cx omega whole square. If you want to non-dimensionalize it, you will take kx outside the thing, then you will get 1 plus c omega by k whole square. So this is transmitted force. And c omega by k we saw in our earlier derivation, that is equal to 2g omega by omega n. So this quantity. So the transmitted force is equal to kx square root of 1 plus 2g omega by omega n. Again expressed in the terms of non-dimensional quantities. And we are interested in the ratio of transmitted force and the disturbing force. So transmitted force, the expression is above, and disturbing force. So the disturbing force is the force at the mass. So in this system, the damper system, at the mass, what is the force? Net force. So the mass at the force we can get from our equation of conduction factor. It is F by xs. Xs was defined as F by k, that is the disturbing force on the mass. That is what we want to determine. K is the spring constant. So x divided by F by k is equal to 1 by square root of 1 minus omega by omega n square, and then 4 by square omega by omega whole square. If you rearrange this thing, you will get F equal to kx 1 minus the expression kx the square root of the expression in the denominator. So this is the disturbing force which is getting from the mass on the mass, the net force due to the effect of all the spring damping, and the transmitted force is this one, kx and this one. So the ratio of transmitted force to the disturbing force is called transmissibility ratio. Transmissibility ratio TR is defined as F transmitted divided by F disturbing. So F transmitted is kx square root of 1 minus 2g omega by omega n whole square divided by, here you will get the disturbing force of the kx is expression inside the square root omega maximum by omega square whole square whole square plus 4v square omega by omega n whole square. So kx and kx will get cancelled out. You get transmissibility ratio is equal to 1 minus 2g omega by omega n whole square divided by square root of 1 minus omega by omega n. This expression that was in the denominator of the multiplication factor. So this is what the formula for the transmissibility ratio. It is again in the terms of the natural frequency, the force and frequency, and the damping factor.